First, we write the balanced reaction equation for the combustion of methane. At room temperature, combustion reaction of common organic compounds leads to the formation of liquid water and carbon dioxide gas. If the organic compound also contains nitrogen and sulfur atoms, then molecular nitrogen gas and sulfur dioxide gas would be found among the products. For the combustion of methane, the balanced reaction equation is simply 1 mole of methane gas plus 2 moles of molecular oxygen gas, forming 1 mole of carbon dioxide gas plus 2 moles of water liquid. Let us rewrite this equation showing all chemical bonds in reactants and products. On the reactant side, in red, there are 4 moles of CH bonds in 1 mole of methane and 2 moles of oxygen-oxygen double bonds in 2 moles of O2. On the product side, in blue, there are 2 moles of C double bond O in 1 moles of CO2 and 4 moles of OH bonds in 2 moles of water. When using mean bond enthalpies, we have emphasized that all reactants and products must be in the gas phase. So for now, we will only be able to estimate the standard reaction enthalpy for the reaction where all reactants and products are in the vapor phase. To carry out the reaction as shown here, we need to dissociate or break 4 moles of CH bonds and 2 moles of OO bonds. We also need to form, the opposite of dissociate, 2 moles of C double bond O bonds and 4 moles of OH bonds. So the expression for the combustion enthalpy is given as delta CH standard, C standing for combustion, equals 4 delta HB standard for CH plus 2 delta HB standard for O double bond O minus 2 delta HB standard for C double bond O minus 4 delta HB standard for OH. Note that since we dissociate bonds in the reactant, we use delta HB standard values for all bonds on the reactant side. In contrast, we form bonds on the product side, hence we use minus delta HB standard for all bonds on the product side. Using mean bond enthalpy values that are appropriate for each bond from the table on the preceding slide, we obtain minus 696 kilojoules per mole for the combustion enthalpy of methane with all molecules in the gas phase. To obtain the true standard combustion enthalpy of methane at room temperature, we need to add to the minus 696 kilojoules per mole the standard enthalpy change associated with the condensation of 2 moles of water vapor, or transformation of water vapor to water liquid. At 25 degrees Celsius, the enthalpy of vaporization of 1 mole of water is equal to 44.01 kilojoules per mole. So the standard combustion enthalpy of methane is minus 696 kilojoules per mole minus 2 times 44.01 kilojoules per mole equals minus 784 kilojoules per mole. For this combustion reaction, the experimental value of the standard reaction enthalpy, or more appropriately the standard combustion enthalpy, is equal to minus 890 kilojoules per mole, about 100 kilojoules per mole more than predicted from mean bond enthalpies. This discrepancy between the experimentally measured value and the value predicted from mean bond enthalpies is simply the consequence of what we discussed on the previous slide. True bond enthalpies and mean bond enthalpies can sometimes be so different from one another that using mean bond enthalpies can lead to inaccurate predictions of standard reaction enthalpies. So we must conclude that mean bond enthalpies are simply not accurate enough to provide reliable values of standard reaction enthalpies. This method should therefore only be used as a last resource for estimations of heats of reaction when none of the other methods can be used.